Um, wait. Okay, that doesn't work. Sure, great, thank you. So just a quick start on, so before talking about black holes, let's talk about where they come from, so stars. So why are stars interesting to us? Because in a way they track the evolution of the universe. So they start forming extremely early in the history of the universe, even before the first galaxies form. And also the star formation history, in a sense, follows the history of galaxies. So the fueling of gas in galaxies, the mergers of galaxies, all of that has an impact on the star formation history. And so understanding this is very interesting to understand the evolution of galaxies. Also, another very crucial aspect for stars is what we call the metallicity. So this is the enrichment of galaxies in heavier metals than, in metals, so in things heavier, metal being anything that is heavier than, that's not hydrogen, essentially, or helium, I think. So whatever is above that is called metals. And understanding, so this has a lot of influence on the properties of stars, and as I will comment, also on the properties of the black holes. And what actually I am interested in is not even the stars, but the depth. So depending on the mass of the star, you can have different outcomes for the end of the evolution. So for the lighter stars, they will typically form white dwarfs. The slightly heavier ones will form neutron stars, and the heavier ones will form black holes, except, we think, for the ones that are somewhere in that range, so that range being a big open debate. So all of those bounds obviously are approximative. Yes?
No, but star cannot be arbitrary massive, no? So can we have star of 200, 300, 400 solar masses?
So if you have the POP3 stars, so which are the very first stars in the universe, I think they can, yeah, so the tail goes to 200-300 solar masses.
Yeah, but no more, not 1,000.
Yeah, 1,000, I think it can happen. So there are like examples of very massive stars, and those are, for instance, suggested to be seeds of the massive black holes. So there are some others like that, but they're extremely rare. So for the POP3 stars, I think they peak around 100, something like that, and the tail can go to a few hundreds. Yeah, so this is the, so there is one of the scenarios that's called the direct collapse black hole, which is we think that it could form directly massive black holes of 10 to the, not massive then, but 10 to the 4 solar masses. Yes. Yeah, and so then they would form a candidate for the seeds of the most massive black holes that we observe today. But this is actually also a very open question. So I also actually also interested in those aspects, but today we're talking a bit more about the stellar ones.
Over lunch we can talk about
Yes. And yeah, so the idea is that so there is this process called parent stability supernova, which, in a sense, if you want, what happens is that when the mass is too large, so the gravitational pressure becomes too large, and it triggers a sort of runaway process that completely disintegrates the star and leaving no remnant behind. And so this depends on the conditions of pressure and temperature inside of the star. And so the idea is that if you are above that mass, somehow you evade those conditions and you can again form a black hole behind. Yes?
the gap in the mass gap between the star and the remnant decreases as you increase the mass of the star. So you increase the mass of the star, basically all of the mass goes into the black hole.
Yes, I will show also something like that. But this also depends a lot on the metallicity.
For very high masses of the star, you don't have metallic star. 200 solar mass, you don't have.
Yeah, so for the most heavy, indeed, so for the most heavy stars, so forming very low metallicity, and so you lose less mass. But you still shed some mass because usually there is still some mass explosion, at the moment of formation. And just to mention that this parent stability is is something that is observed in simulation, but never has been observed in practice. It's very speculative, and we expect that one of the ways we could understand that is exactly through the observation of black holes. And so all of these objects that are here, so the white dwarf neutron star black holes, that's what we call the compact objects. And why are we interested in them? So as I said, these are the outcomes of stellar evolution. And the thing is that these objects are typically very faint or even completely dark for electromagnetic observation. So a black hole, unless it's surrounded by matter, you cannot observe it. And even white dwarfs, they do have an emission, neutron stars as well, but it's very faint. And typically, we have no observation, I think, at all outside of our galaxy of those objects. I mean, with electromagnetic observations. But these objects, if they are in a binary, they emit a lot of gravitational waves. And so just to give an idea, you can, if you just do some computations, you find that the amplitude of gravitational waves scales in this way. So this being the total mass of the system, the distance to the source, and this is the separation between the two objects. And so in a sense, with gravitational waves, it's not just that we're interested in compact objects, but it's also that we can essentially observe almost only compact objects because we want that thing to be as low as possible so that the amplitude goes higher. And so you can, if you just plug in some numbers, you'll find that for double white dwarfs, the amplitude of the gravitational waves that they emit is 100 times larger than for stellar binary, so with keeping the total mass fixed. It's 70,000 for binary neutron stars and 300,000 for black holes. So you can see that those objects emit way more gravitational waves than just compact regular stars, and this is why we actually don't expect to observe regular stars. And now, so this is, you probably have already seen this plot a couple of times, but here is showing in blue all of the systems that have been observed by the LIGO-Bicocca collaboration up to the third observing run. And in red, you have, so these are all the black holes. Here in orange are the few neutron stars that have been observed. So you have the progenitors and then the final black hole every time. And in red are the black holes that were observed in electromagnetic waves. And what you can see already is that in 10 years of observation, well, actually that was after, let's say, 5-6 years of observation, we already had way more black holes observed through gravitational waves than we ever had with electromagnetic observations. So for neutron stars, we're not quite there yet, but with time, eventually, we'll get more data. And as you might be aware, actually, so this is the data up to the third observing run, and next week should be coming the data for the fourth observing run, which should the first part of the fourth observing run, which would be 100 more detections or so. And so we expect that this will increase a lot our statistics and analysis. And so just a quick word on the detectors that we have. So currently we have LIGO-Bicocca that are running, and they detect here in this, so from 10 to a few thousand or so, a few hundred hertz. So well, this is the Virgo detector, so this interferometer. In Italy, there is also LIGO in the US, and in the future, we expect to have the Einstein telescope and the Cosmic Explorer, which, as you can see here, will increase the sensitivity a lot, allowing us to observe up to redshift 20, so the very first black holes. We have at lower frequencies, so pulsar timing arrays. So we had the talk yesterday by Gabriela, which observes, so here, so since the frequency of gravitational wave scale essentially as 1 over the mass, the total mass of the system, at much lower frequencies. Here, the nanohertz regime, you observe much heavier systems. Here, we're talking about the inspiral of massive, supermassive black holes. And here as well, with the square kilometer array that should start from 2030, we expect, again, to observe way more things, and to improve our measurements. And right, so finally, which has recently been approved by the European Space Agency, we will have the Laser Interferometer Space Antenna, LISA, which should start from 2035 and will complete here the frequency band, observing in the millihertz regime. So one of the main targets of LISA are what we call the coalescence of massive black hole binaries, so more, whereas PTA is more observing 10 to the 8, 10 to the 10. Here it's more 10 to the 4, 10 to the 8 solar masses. So it's different systems. They typically live in lighter galaxies, so which actually, and also we can observe up to much further redshift. So it's really galaxies that we have never even observed eventually in electromagnetic observation. So this is really a completely new information that we will have. But actually, what we'll observe the most with LISA are the galactic binaries. So those are the binaries, mostly double white dwarfs, that are in our galaxy. All the simulations agree that there should be around 10 to the 7 million, 10 to the 7 of them in the galaxy. And those sources, so they will form, most of them at low frequency. When they are low frequency, they actually form also a stochastic noise, which is actually a foreground. It's not even a background, it's a foreground, because as you can see here, in some frequency band, it dominates over the instrumental noise. And on top of that, we expect that around 10 to the 4 of them should be also individually resolvable, so you can measure the parameters of them individually. And so all of this makes the LISA data analysis extremely challenging because you need to infer everything all together. This is what we call the global fit. So you need, and on top of that, there are also some other possible sources that I haven't mentioned, but you will need to infer the parameters of all of the 10 to the few systems that we observe all together. So today, I will not be, so I'm actually also very interested in massive black hole binaries, galactic binaries with LISA and also PTA, but today I will be focusing more on that part of the gravitational wave spectrum. But I'm happy to discuss this at any other moment. So what I'm talking about today is how can we use gravitational observation to learn about the stellar evolution and binary formation, focusing on stellar mass black hole binaries. So I will not be talking much about neutron stars, and also not double white dwarfs. So I will just discuss some results that we have on the current data, although from next week on they will be outdated, but I will discuss a bit of what we expect that this new data can bring us. I will also discuss some cares that need to be taken when comparing this inference to astrophysical predictions. And finally, if I have some time, I will discuss some techniques that, so more data analysis aspects also for this. Okay, so the idea is that there are two main scenarios that have been proposed for the formation of stellar black hole binaries. So the first one is the isolated scenario. So these are black holes that are, you have stars, stellar binaries that are somewhere in a galaxy, so what we call in the field, so they don't interact much with the environment. They evolve, so there are different evolutionary paths that are possible. So there is a so-called common envelope process or stable mass transfer. Well, essentially they interact, and at the end of the day, they form each of the stars can eventually form two black holes. So this is really the tail of the distribution of stars that will form those stellar black hole binaries, and that they finally merge. And one of the things is that if you look at the scenario, so there are a couple of predictions, which is one of them is possibly this existence of this mass gap between 60 and 120 solar masses. Also because they mostly, so they interact for a very long time, we expect that the spins of the black holes will be aligned. And also for the same reason, because eccentricity tends to decrease with time through gravitational wave emission, we expect that there will be quasi-circular binaries. On the other hand, the other big main scenario that has been proposed is what we call dynamical formation. So this happens in more dense environments, like stellar clusters or AGN disks. And there, so the idea is essentially that you have one black hole that comes perhaps from this, or well, has been somehow formed from the collapse also of a single star perhaps, and eventually meets another black hole and they pair. So as you can imagine, this, because gravitational interaction is so weak, this is an extremely rare process, but if you have dense environment, this can happen. And so one of the predictions that we expect for these channels is because you can form, so you can repeatedly have mergers, you can increase the mass of the black holes that you form. So we expect to have heavier black holes that come from this sort of formation scenario. Also because they meet in a completely random way. So if it's in a stellar cluster, so nuclear star cluster, globular cluster, we expect the spins to be completely random oriented. So we expect that they could be anti-aligned or whatever. This is not exactly true for AGNs. Yes, sorry. Okay, sorry. So it's not exactly true for AGNs because there is a preferred angular momentum direction in an AGN disk, and so we expect that the torque that is induced by the AGN disk should align the spins of the black hole. So this is a bit different. And just finishing, also because they form in such random way, so by capture, they can have much larger eccentricities. Yes? So it's because gravitational interaction tends to align spins. So if you leave any system long enough to interact gravitationally, they tend to align. Yeah, yeah. That's what happens, yeah.
I thought it was the interaction with the marker in the common envelope rather than gravity doesn't align spins. It's the marker in the common envelope.
So gravity does end up aligning spins, I think. It does damp precession. It's just like if they form if they form so close here in the dynamical scenario that they are. Well, from the equations of more, but for me, it's like it's the fact that here they interact for a very long time, whereas here they can form already very close with completely random spins. So you don't have the time to interact.
It was the gas of the chemical envelope that tend to align the spins, the friction of the gas, not gravity, fundamental gravity itself. But
Okay.
I'm not 100% sure.
Okay.
You might
Let's.
be right.
Well, I will
Check.
look again. Yeah. It's true that yeah, matter interaction also here helps. Yes. Very good question. So this is one of the things we want to understand now. So I mentioned that one of the reasons why you need to have a dense environment is to increase the chance of capture. There's also another thing which is the kick, because when black holes merge, in particular if they have isotropic spin, they can there's a kick on the remnant, and if the medium where they are is not dense enough, this black hole can get expelled from the environment. So this is one thing that would tend to decrease the chance of having higher generation mergers. Now, in simulation, so people can have some second generation, third generation black holes that form, like that they manage to retain and contribute to the population, but it's essentially unknown. In AGNGs, so one of the things that has been proposed is that there is a thing called the migration trap. So it's a place where, so there's like in the inner part of the disk, you have a torque in one direction. In the outer part of the disk, you have a torque in the outer direction, and you have sort of a place in the middle where they cancel, and that black holes could gather there. And so there you could eventually form a lot of higher generation mergers. And this is something that has been suggested for some of the properties that I will discuss later. But as I say, all of this for now is speculative.
Waveforms would be, can you distinguish these two processes as a waveform?
Well, so that's actually that's what I'm getting to, is that from a single merger, you cannot, so you essentially, you can in a case which is in here in particular. So if you are in a non-trivial environment, such as an AGN disk, this might leave imprints on your waveform. So the presence of matter, the presence of a massive black hole at the center of the galaxies, all of these can, so you have a peculiar motion which can affect your waveform, and you might be able to measure that and say, oh, this then. But the thing is that all of this is also very degenerate with modifications of GR, for instance. So from single experiments, because otherwise, I mean, the gravitational theory to describe the waveform is the same in both cases. Now, it's true that, as I said, if you observe a system with isotropic spins, so with anti-aligned spins, you would not expect that this comes from this scenario. But so the point I will make now is that actually what you need is really the global information. You don't want just a single system. From a very single system, it's very hard to tell anything, except, again, if you measure environmental effects, the point is looking at the global population.
Yeah, but the rule of thumb is speed. If there are computation, that's usually taken as a sign of.
In hardening phase, do you have any emission of gravitational wave?
Here?
No, on the right, there's something called hardening.
Yeah, sorry. It's because in many scenarios, you need something to bring the binary. You still need, even after the capture, you still need something extra to bring the binary close enough. So this can be typically interaction with third bodies, which will extract energy. They can also exchange. So one thing that can typically happen is that you will exchange the lightest for the heavier. You keep the two heavier black holes among the three of them. And all of this brings the binary closer together. But so this really can leave some eccentricity, but it's very hard to measure eccentricity with current detectors because it goes to zero by the time of merger. And as Ricardo said, also spins. However, you can go see any. I mean, the whole point here is that you can go see any astrophysical modeler, and he can cook up a scenario where you will have randomly aligned spins. So, I mean, it's true that, as I say, in general, we don't expect that. And so this is why looking at the properties of the population in general is where you can extract the most information.
But usually the hardening happens outside the light of energy.
Yes, yes.
Right before the merger.
Yeah, sorry, because so the hardening is exactly what makes the binary merge within a Hubble time. Otherwise, you don't have that merger. Also, another thing just to comment on is the role of metallicity. So this plot is showing the mass of the remnant, of the black hole remnant, as a function of the initial mass of the star, so the zero age main sequence mass of that star for different metallicities. And so what you can see is that if you look, for instance, at the purple band, that's where, so the lowest metallicity, that's where you tend to form the most massive black holes. As you increase the metallicity because of stellar winds that tend to expel a lot of matter from the star, you don't form that heavy black holes anymore. And so a lot of mass is shed and you don't form black holes that are that massive. And here it suggests so that there would be a mass gap. So here, because of this parent stability process, you wouldn't form black holes anymore. And if you have a star that is massive enough, you could form again black holes, but above the mass gap. So I think this is due to, so there's another process also that is called pulsational parent stability. So instead of having a complete explosion, you would have like sort of pulsation where the star would lose some of its matter, but then it would still form a black hole at the end. But it would be less massive than you would expect originally. Yeah. Okay, so as I was just advocating, now I think the way to understand, what's the role of this scenario, what's the role of this scenario in general, is really to look at the global distribution. So when we combine all of the observation, how does the distribution of masses, how does the distribution of spins look like? And the way of doing that is through what we call the hierarchical Bayesian analysis. So the idea is you need initially to have a model for the distribution of your parameters. So here, for instance, the two masses of the black holes, the spins, and the redshift. And typically, you take a model which depends on what we call here the hyperparameters. And so those hyperparameters are three parameters that you want to infer exactly by combining all of your observations. These population here can be, so we typically speak about astrophysical models. So those are models that are motivated by astrophysical simulations or astrophysical theory eventually. So yeah, otherwise, so that we have what's called the parametric models. So those are the ones that are typically relying on simple functions. As I will show one example, but the most famous of it is the power law plus peak of the LIGO-Virgo collaboration. So those are very simple analytic functions that can be where the parameters still have some vague astrophysical meaning. And finally, the last one is the non-parametric. So those are more sophisticated, flexible models that can require less a priori assumption about the distribution, but you have much more parameters and you completely lose the meaning of the parameters of your model. So they just here really as for you to represent your function. I will give more concrete examples. So that, just to mention, so the advantage of astrophysical models is that, well, they are astrophysically motivated. However, they are more rigid because your simulation predicts something. You might not have the flexibility to capture what is in the data. And also using it in practice on data has a bit of a problem because you need to be able to evaluate this quantity, so the density function itself. And usually when you have simulations, what you have are samples from your population, and then you need a way to obtain, so you can use eventually a KGE or some neural network to obtain that density, but that still requires that extra step. Sorry. So this is, you need to assume a model for the distribution of masses, spins, and redshift of the black holes.
What about the mass of the star that gave rise to the black hole? How do you get that?
So that is in, so this is more by, no, I talked about black holes. I mean, you could always have a model where you will start from an initial mass function for the stars and do the whole propagation and those parameters. And there are actually some people that do that, and they will fall more in this category. But they have the caveats that I mentioned, which is you need then a way to, from the output of the simulation, to get an interpolant for that. And it needs to be efficient. Yeah. Here I'm interested in the mass of the black holes, but then the idea is once you get that, you can compare so you can take an astrophysical model and compare what does it predict for the population of black holes given the initial conditions for the stars. And the way of doing this, so now once you have your model, you need to plug it in this whole formalism, which allows you to obtain the posterior distribution on your hyperparameters, accounting both for selection effects and measurement uncertainties. So you get a formula like this. So this is just the prior that you have on your hyperparameters. This is the individual event likelihood. This is your, sorry, I dropped the pop here, but this is the P pop of your model. So here I just use this theta for shorthand notation. And this is what we call the selection function. So this is the integral of over your population model of the probability of detection of a single event. So this tells you what is the fraction of events from your population model that you expect to detect. And then you plug all of that in a Markov chain Monte Carlo, and you obtain the posterior distribution on lambda.
So capture lambda are the parameters of the hyperparameter of your population.
Exactly. So, I mean, in the power law plus peak case, which I will just show, is the exponent, the position of the peak. And so this is the result that you probably have already seen, which is the result, the fiducial analysis of the Ligo-Vigo collaboration on the GWTC3 data, which is here assuming so a power law plus peak. So, well, it's a power law with a peak somewhere, and so the parameters, as we just. So they have the priors on the hyperparameters, yes. So they usually.
Because, for instance, if you assume that there shouldn't be any black hole in mass gap, that would be a prior, but you don't assume that.
No, they don't. And but actually, this model, one of the problems, it doesn't really allow for a gap. So the analysis is cut at 100 solar masses by hand, yes. This one is not cut by hand. So this actually, there is a smoothing function, transition function, to make it go to 0. So this is inferred somehow, but this one is cut, yes. But yeah, so but actually, so that's actually where I want to get to, is that when you choose, in particular, when you choose a parametric model, it is already quite a strong choice. So for instance, such a model doesn't have the flexibility of showing you a gap. So if you expect to have a mass gap, well, okay, you could say that because the M, so there is a M max for the power law, so up to where it goes. And you could always say that it goes here. So you could kill your distribution perhaps around 60 solar masses, but you cannot then restart it later. So in that model, indeed, it does not allow for that flexibility. But I guess the point is that essentially, well, what people often end up doing, you try a bunch of models, and you end up using what seems to give most meaningful results. But I will also discuss a bit more of that. So the dashed lines show the 90% contour, and the full line shows you the mean. Yes. No, so selection effects are taken into account. I mean, if they're taken correctly into account, I mean, it should be fine, but in principle, it's taken into account.
If you look at the detecting mass distribution, it's completely different. It's peak and it grows as it should be.
So most of the events that we have actually are around here. So this is where most the observed, you will actually see it also later, but the observed distribution peaks around here. Here you have much fewer events, but because the probability of detecting them is lower, once you do the analysis, it enhances that peak. And so, well, we have some features here. So one of them is this peak around 10 solar masses, which, well, we think comes from isolated binaries, so from single binary star evolution that form these black holes.
By the way, the black holes we see in our galaxy electromagnetically.
Yeah. Well, then there are questions about the spins, right? So people argue that the black holes that we observe in our galaxies in X-ray binaries tend to be more rapidly spinning than the ones we observe. So then there are questions. So in terms of mass, I think they're mostly compatible. In terms of spins, it's very open. But in terms of spins also, I think X-ray observations are perhaps not that accurate yet. So it's an open question. But yes, those would be the closest ones to what we have in our galaxy. Then there is this other peak around 35 solar masses. And well, this I think came a bit as a surprise at the time for the community, because this peak, the idea of having a peak there was to represent sort of a piling up of black holes before the parent stability gap. But the parent stability gap was thought to be more around, well, at least 50, 60 solar. So there is a lot of uncertainty on where it happens, but we didn't think it could happen at 35 solar masses. It could also be due to pulsation or parent stability that I mentioned, which happens at lower masses, for the black holes, and instead of having black holes here, so completely destroying the black holes, you would have this pile up around 35 solar masses. That is a possibility. It could also be that there is another formation scenario that is contributing. So you could imagine that, if you look at isolated, it would go to zero, and dynamical would start contributing a lot more around that masses. That is perhaps also a possibility. Just to mention also, because dynamical capture is also much more efficient for more massive black holes. So you do expect that the black holes that you will have through that scenario are more massive. Right. And now I want to show, so the black line was the standard LIGO-Virgo result. Here I'm adding now this red line, which is our analysis on that data. So what we did here is that, well, we represented the mass function as a piecewise power law. So essentially, you have some knots to where so you try, so yeah, it's essentially that between each of those knots, your distribution follows sort of a power law. In log-log, that means it's linear. And what we do is that we infer both the position of the knots.
Single power law in each
In
bin.
each bin, it's a single power law. But what we infer both the position of the knots and the number of knots. So we use a technique called reversible jump Markov chain Monte Carlo, which allows you to infer both the parameters and to vary the dimensionality of the problem during sampling. And so why is that actually interesting? Because I mentioned earlier on that non-parametric models, one of the disadvantages is that they can have actually a lot of parameters. And it's sort of impossible to know a priori how many parameters should you use, which complexity. And so here, in a sense, the complexity of the model is decided by data itself. We don't impose it beforehand. And so what you can see is that, well, we agree quite well on some features, although, so here we have a much narrower peak around 10 solar masses, which is also happening at higher masses. But a thing that is to be taken into account is that the LVK result here is largely influenced by the choice of the model. So the way, so they do this power law plus a smoothing function, so on and so forth, this influences a lot the shape of the function here. So again, it's a prior choice that you're doing. We also find sort of a peak here, although at slightly lower masses, but well, within arrow bars, it's compatible as well. And the other thing is that we have a feature here possibly around 20 solar masses. And so, but here you can see, if you look at the arrow bands, that it's telling you it could be actually two things. Either there is a peak around 20 solar masses, and this has been suggested that it could be due to repeated mergers of those black holes. So you'd have black holes around 10 solar masses that merge again, and you would have a pileup around 20 solar masses, so in a sense, harmonics of black hole mergers. Another thing that this could be as well is, if you look here, the arrow bars are compatible with the rate going very low, and this could also be due, not that you have properly a peak, but more that you have a gap around 15 solar masses. And this has also been discussed, as it could be from the formation of stars, you would have sort of a discontinuum of the condition of the stars where you could form black holes. So you would have stars that are low enough in mass that would form black holes, then as they increase in mass, they wouldn't form black holes anymore, and as they increase in mass again, they start forming black holes again. So I think that actually also ended up discovering that this whole black hole formation, even for isolated stars, is extremely not well understood yet. So the whole supernova process, so on and so forth, is extremely uncertain. And it could be that so you would form the black holes around here, and then you start forming black holes again around here, but you wouldn't form many black holes around here. So, however, as I pointed out, the uncertainty here is extremely large. And, well, I think this is one of the things that the coming data and so on will inform us a lot about. Okay, so moving on with this, the thing is that in many analyses at least, the population model is assumed to be separable. So that means we don't allow for correlations at the population level between your mass, the spin, and the redshift of the black hole. However, we do expect that they should exist in nature. So, well, I think the one that people are the most interested in the mass and redshift. So we do expect that the distribution of black holes should evolve with redshift because evolution of metallicity. So metallicity was lower at high redshift. You would more easily form more massive black holes. Also, dynamical formation, for instance, is expected to contribute more at lower redshift than higher redshift. And so all of that should lead to evolution in redshift of your black hole mass function. Also, for instance, another correlation that people are very interested in are mass and spins. So we expect that through repeated mergers, you would form black holes with larger spins, just because so if originally they were isolated black holes with 0 spin, after they merge, they have typically a spin of 0.7. And so if that black hole contributes again to another merger, you would expect to observe that this black hole has a spin of at least 0.7. And so this is also a way to understand if the black holes that are more massive, if they tend to have larger spins, it would be a sign that they are coming more from the dynamical formation. So the point that I'm trying to make here, and there are actually a lot of many other correlations that you would expect between the parameters of your population. So the point I'm trying to make is that looking in the higher dimensional parameter space is actually how we can really extract all of the astrophysical information that we have in our data. Looking at marginals, well, first, it can end up introducing a lot of biases because this model can be technically wrong. And second, you lose a lot of information. So so Ricardo would probably not be fully agree with this, but what has been found to be the most robust correlation in the current data is the one between the mass ratio of the black holes, so the ratio between the two masses, and these specific spin parameters. So this is actually the spin parameter that we measure the best for gravitational waves. So it's the projection of each of the black holes that you weight by their respective masses. On the orbital angular momentum direction, and you weight them by their respective masses. And so typically we would expect that black holes that form dynamically would have very low chi-effective, because you can see that, well, if you plug here, if the spin orientation is random, it tends to have chi-f very close to 0. You would have chi-f larger to 0 if your spins are aligned, for instance. And so people analyzed the data, assuming that, for instance, you have a Gaussian distribution for your effective spin, but where the mean and the variance of your distribution depend linearly on Q or log Q. And they find, so this is what they inferred, Delvicke inferred for the mean of this distribution as a function of Q. And you can see that you have quite some strong indication that it would evolve with spins. And this would result in a shape like that for the chi-f-Q distribution. And the point is that this was actually an unexpected correlation. So I mentioned. Oh, sorry, yeah, it's cut. So this is Q, and this is the mean, so what they inferred. So essentially, they inferred those parameters, and they plot here the curves. And so this was an unexpected correlation, which was not anticipated by astrophysical models and so on. And so it has triggered a lot of discussion about how this could happen. So one of the scenarios that has been suggested is binaries that form in the AGN. So there is this migration trap that I mentioned earlier, where you could have a lot of black holes gathering, and exactly through nth generation merger. So you could have a black hole that is there, essentially, and keeps on merging with incoming lighter black holes. So this would make the black hole that is there heavier, decreasing here the mass ratio. And at the same time, it would have larger spin, because its spin is usually aligned with the spin of the disk. And so this could be a way where you could form that. Another scenario that has also been suggested is through stable mass transfer in isolated binaries. So the point is that if the mass ratio is larger, so the rush lobe, the rush lobe is essentially the radius where the star is gravitationally bound, and so the rush lobe increases, and so that decreases, and so that means that the stars, starts accreting from one of the stars starts accreting from the other star earlier on, and so that spins up the most massive star. And so you could have also a scenario where you'd form a more massive star that is highly spinning with a lighter star, more massive black hole that is highly spinning with a lighter black hole. But again, all of those are scenarios that have been proposed that could reproduce such a correlation. I also have to mention that some people have discussed that this correlation could be due to systematic effects in the inference, so just in parameter estimation. So that it could be because our waveform models are not accurate enough, and so they introduce a spurious correlation between the mass ratio and the effective spin. Well, the LVKD try to assess a bit the impact of systematics. They find that this is kind of robust against systematics, but it's still also an open question. So now I want just to mention what we have done so regarding this. So this, as you can see here, is a more parametric model. So you assume a form again for your correlation, and you try to infer it. And we extended our approach that we had for the mass spectrum. But now the thing is that, well, essentially what we did here is some sort of fancy interpolation technique. The problem is that interpolation in 2D is not, or higher dimension, is not as trivial as in 1D because, for instance, if you want to do a grid of points, then every time you add one x coordinate, you need to add all of the y coordinates that go together, and that makes your parameter space increase a lot. So it's not extremely efficient. So the approach that we took is that if you think of this, for instance, here it would be Q, and here your effective spin. What we would have is a bunch of points that are in that space. So these are the equivalents of those knots here in one-dimensional. And we use a technique called Delaunay triangulation to build triangles from these points that are here. And so Delaunay triangulation is a sort of optimal triangulation method where you avoid forming triangles that have too small angles, so on and so forth. And this allows you to triangulate your space from these points that you have. And once you have that triangulation scheme, you can do barycentric interpolation to interpolate your function inside of each of the triangles. So in our model, our parameters would be the position of those points, the value of our function at those points, and the number of those points. And so the idea is that, again, this allows you to have a sort of optimal complexity to represent your data, and also that everything is adapted to the data itself. So we don't pre-decide on a grid, we don't decide any of the structure, we let everything be adapted to the data itself. And one other thing that I think is important to mention is that thanks to this technique, we actually have already in 2 dimensions around 2 orders of magnitude fewer parameters than other approaches that try to do similar non-parametric methods for 2-dimensional distributions. And well, the quality here is actually not that great, but if you follow here, you can see that this yellow, yellow color kind of follows. So these are the contours from the LIGO-Virgo result, and you can see that our yellow color follows mostly the same direction. So essentially, we are also recovering this correlation between Q and chi effective with our model, which is way more agnostic. And well, so here we apply now the same model to study the evolution of the mass as a function of redshift, and this is what we find. So a very important disclaimer is that what I'm plotting here is the median of our distribution. So you would have to think of this really as a sandwich. So you would have also a 95% quantile, a 0.05 quantile, which have error bars. And so if you look at the median, it suggests that you would have first a population here at lower masses that are also at lower redshift, and you would have this population here at higher masses. So I don't know why the quality on that screen is a bit worse than on my computer, but well, I guess you can still see that he is brighter than here. And so this would suggest that there is a second population of heavier black holes that are also at higher redshift than the first one. However, as I said, you have to account for error bars. So here I'm not plotting them also because it's a bit involved to show that in 2 dimensions. And the point is that there are hints that there is these 2 subpopulations, but the current data is not enough yet to inform us on that. And we expect that with the upcoming data, we will have more information on that. Okay, I also decided not to go through a full review of all of the results on TWTC3 because there are like quite tens of papers that have been written on those data, and well, doing the complete review would be perhaps a bit too much. So I want to talk now about a slightly different question. So still on this whole population analysis business, but now once you've done all of your analysis, how can you compare in practice to astrophysical predictions? And so here, I'm showing again, so this is the power law plus peak result from the LIGO-VICO collaboration. So the bands show you the 90% confidence interval, and the full line shows you the mean that by the collaboration. And here I'm plotting the distribution that is predicted by some astrophysical model. But the difference is that the dashed one takes all of the black holes from the simulation, so from redshift 0 up to redshift 20. The full one, no, so the histograms show the prediction of the simulation. Sorry, okay. So we have so we took the prediction from one astrophysical simulation, so one population synthesis model. So this is the one from Arcaceda et al. So yeah, sorry. And we plot the prediction of that population synthesis models using all that is predicted by the model from redshift 0 to 20. You mean they have sort of calibrated the parameters? Yeah, but so it doesn't, yeah, sure, but it doesn't, so the point that I want to make here is that if you take all of the prediction of that model, and now the difference with the full line histogram is if you take only the predictions up to redshift 1. So the dashed line includes all of the predictions. So you take your population synthesis model, you plot the of all of the mergers that you predict. The full one, you plot the distribution in mass only of the ones that happen up to redshift. And you can see that, well, exactly perhaps because also the model has somehow been calibrated to data, but there is actually quite some difference. And that when you account only for the ones up to redshift 1, they actually match data better than the ones that are the black holes in the universe. And you can also understand that because if you look at the evolution of the rate of, well, of black holes as a function of redshift, so the blue line is the result that has been inferred by the LIGO-VICO collaboration. So they assume that the rate evolves as a power law, and they infer the power law index. This sort of yellow reconstruction is what I also did using the same data, but a non-parametric, essentially the same non-parametric approach than there, which is so more flexible. And you can see that the error bars become extremely large above essentially redshift 1. And this is a distribution of, so these are, when you pile up all of the posterior distribution from all of your mergers, you can see that essentially, well, what's happening is that we have no information after redshift 1. And so also the mass spectrum that we're inferring from the data is actually informed only up to redshift 1. And so this is why when you compare to astrophysical simulations, you kind of have to take that into account. Because otherwise you might think that your model is performing worse than it really is, whereas perhaps if you constrain to the domain of validity of your inference, you will get something that is better agreement, or well, or the other way around. But so the whole point of these plots is to exactly show that one of the problems of these parametric approaches is that, again, they're making quite strong prior assumptions, and they don't have a well-defined domain of validity. So you don't know up to where they are valid. If you do a non-parametric reconstruction of those data, so as you can see here, what you will typically get is that errors broaden, and so that reveals your lack of knowledge. But for having worked with these things quite a while, I have to say also that this is a bit of a pain to make sure that your non-parametric models have the desired behavior. And it kind of has to be sort of, you have to check, you have to enforce it by hand, that you don't you're not finding information where you don't have, so on and so forth. Yeah. Yeah. Sure. But I mean, but the question is like, you can take parametric model, you will complicate, so on and so forth. But the question will always remain, what is the validity of your model? Yeah. So the point is, one of the ways of addressing this question is limiting yourself to the domain where your observations are. And the most natural way of doing it is, instead of looking at the astrophysical distribution, to look at the distribution of events that are observable. And so just going back to the equations, the clean way to do it is, so this would be your, so this is the function, the posterior distribution on lambda. So again, lambda here, the hyperparameters of your model. This is your selection function that I introduced here again. And what you can do is just, well, it's just a clever trick, but you multiply and divide by this p det. So this is the individual detection probability. And you define, so you realize that this quantity here is exactly the observable distribution. So this is the astrophysical distribution times the detection probability, and this alpha lambda is exactly what normalizes this quantity. And you end up that you can infer, so if now lambda are parameters of your observable distribution, you can infer your observable distribution. However, and that's the key point here, you still end up with this term, which is sort of a selection function. And so that means you can infer the observable distribution, but you need to account for selection effects also there. You cannot just neglect completely that there is selection in your data and then do inference, and afterwards we reweight by the selection function. You need to take into account even at that stage of your inference. And so the reason why I'm spending some time on this is that in our community, this was some sort of a not very well understood question for a while, because so often people were doing analysis without that term here. So there were some discussions showing that, well, this would lead to biased results, so on and so forth. And again, the key point is you can do it, but you cannot get rid of selection effect even at the inference level of the observable distribution. Now, one computational advantage of this is that, so typically what we do, so if you use Bayes' theorem to rewrite this individual event likelihood as the posterior, single posterior, you end up with this. And so typically, though this is a posterior for each of your events, and you have samples from each of your events that we use to do Monte Carlo. And the point is that what I'm trying just to get to is that you actually know where are the points that you need to compute this quantity. You can pre-compute all of those numbers and then use it in your inference. Whereas in the standard analysis, what you need to compute is this number here, which depends on your hyperparameters. So that means that while sampling, you need every time to recompute this quantity. Whereas here, you need to compute, they don't depend on lambda, they depend only on the single event parameters. So you can compute all of them before, store them, and do your analysis. And if you do that, so this is what we did on the DWTC3 data, you get, so the green results, again, the 90% confidence bands. The blue one is showing the LIGO result if you reweight the results by the single event detection probability. And the red is the prediction of the population synthesis models that I was showing before if you reweight by the detection probability. And you can see that, as expected, you have actually much less disagreement between those models. Well, not as expected, perhaps, but as what I was showing before was already hinting, you have a much better agreement between the population synthesis model and your observable distribution that you would have thought if you look only at the astrophysical distribution. And again, the reason for that is that in this sense, your inference is bounded to the domain where you have information. You're not extrapolating information from your model. And then, and finding spurious features in your data. And this is now, so this is the mass distribution, this is the redshift distribution, so this one, well, essentially it falls down to 0 because of selection effects. And as you can see, so both of them agree quite well. And it's also, well, actually in agreement somehow, but because the error bounds are large, with the standard inference from the LVK.
But this population model is a mixture of common envelope and dynamical capture?
Yes, sorry. So this population synthesis model combines both isolated scenario and dynamical scenario.
And some ad hoc fraction or some astrophysically motivated?
So it's all, so they evolve the galaxies, they follow somehow the star formation history in the galaxies, and of course there's some they have to put behind some prescription, but yeah. Yeah, so that's really what, so Manuel Alcaceda and his group, they are going to release now the new version of their model soon, and this is really what they've been working a lot on. Right.
Sorry, can you hear me?
Yes.
On Zoom, I have a question.
Mm-hmm.
So when you reweight the LVK analysis
Yeah.
to observable space on the mass distribution, The error bars for high masses, they broaden very much. They get larger.
Yeah.
Uh, why is that? Because you're still using a parametric model, right? For LVK.
Right. So, um, so I think this is somehow capturing the fact that you don't have much information there. So even if you did a, well, okay, let me think. I had not thought of that before. So you are convolving again with the selection function, and I think it broadens a bit the behavior of the observable distribution with respect to the astrophysical distribution in that regime. That would be my, yeah, my first thought here.
So that's the same reason why in observable space you can measure the rate at high redshift with better accuracy than in the astrophysical space. I mean, if you look at the plot at the bottom right corner, the error bars at high
Correct.
redshift, they're very smaller than the previous plot that you showed.
Yeah, so I think one of the big differences is that in the observable space, this does go to zero, right? Whereas like in the astrophysical space, you have absolutely no idea how this should be, how it behaves.
Oh yeah, that's right.
So this is really the selection function that is driving the fact that this goes to zero there. Whereas here, the selection function doesn't drive the fact that it should go to anywhere. It just tells you that the selection function gives you some information up to some redshift because you know that if there were many, many, many events there, you would still be able to detect some of them. But at some point, your selection function doesn't help anymore because you know you're insensitive. Whereas here, now, again, I think so. Also, perhaps an important point is that the model that we used here for the important thing is that the model we used here is also a parametric model for simplicity, and so it also perhaps doesn't. Yeah, actually, that's a good point. Perhaps it doesn't fully capture the fact that it should broaden perhaps a bit more than what we're showing here. Although I do think that the selection function dumps it quite heavily there. So I think this is mostly selection function driven. Sorry, does it make sense?
Yes, yes, thanks.
Okay, so just one comment, so more technical comment on this. So if you pay some attention, you will, so as I say, this term here is in the denominator, and this detection probability can technically become very low. And that means that once you do your Monte Carlo estimators, because this can kind of complicate a lot the convergence of these estimators. So what we did here in this analysis, I have to do an important point, is that we used, so there is an emulator by Thomas Callister that to compute this quantity. So we took that emulator, and this is the value of the PDET, the single event detection probability, on all of the samples of all of the events of the O3 data. And you can see that it kind of falls like that, and then you have this. And so this is a bit of an ad hoc prescription that we took, which made it that essentially the emulator was accurate up to around 10 to the minus 3. And so we discarded by hand all of the samples that were before, that had lower detection probability, arguing that those are, that the emulator is not accurate enough below 10 to the minus 3. And well, to make that more valid as an assumption, we also estimated what would be the accuracy that you need for your analysis on the detection probability. And you can estimate essentially that the accuracy you need is 1 over the number of events that you expect in your observable volume. And you can estimate that by looking at this quantity, which you can estimate from your real data, and we estimated that it's around 10 to the minus 2. So it's a bit of a happy coincidence, but we expect that the fact of having essentially be harming our inference too much. Right. Actually, I mean, this is also, since there are people also with different expertise in the room, this is something that I've been wondering for a while, is because I'm not sure I haven't. in other fields, I would be curious to know how people do that sometimes, because I've seen in some papers people inferring the observable distribution in cosmological cases, so on and so forth. But I have the impression that often people take the likelihood times the observable distribution, and I don't know if that. So well, what this says that is not fully correct, and at the same time, I don't think that. I think it's hard that we just found that by ourselves right now. So if anybody has some thoughts, I would be curious to know. So as a summary of
Sorry,
yes.
I have another question on the point that you made on the previous slide. So your point is that as long as um, your emulator is accurate enough with respect to like this metric that you have, then there's no problem in discarding these very rare samples from
Yeah. Yes.
the model some that wouldn't bias the analysis.
Exactly. That I mean that's the estimate, but I have to admit it's more of a back of the envelope computation than a full assessment of this. Okay.
Okay, thanks.
Right. And so, just commenting on so that I think one of the main advantages of doing all this whole comparison between data and astrophysical predictions in the observable space is that you really restrict your comparison to the domain where your observations lie, and so where the information lies. You're not doing any extrapolation of parametric models. Also, there's a fact that more again of a technical aspect, but the fact that the distribution goes to zero outside of your domain of observation, if you want, you could do all of the analysis that I did here with non-parametric models, and so for instance, that one that I use or something like that, and the fact that your distribution goes to zero outside of your domain of observation makes things a lot easier to model, I have to say. On the other hand, so the fact that you could have these low detection probabilities could cause your Monte Carlo estimators to have large variance, which is bad. And also, it's not perhaps that trivial. So in principle, you could say now that the astrophysical distribution is the observable divided by the detection probability. But for the more or less the same reason than here, when we tried that, for instance, it doesn't give fully convincing results. So this is something that needs to be better understood. What are the conditions under which you can obtain the astrophysical distribution from the observable distribution? Okay, so I don't know how I'm doing with time. Okay, so I try to do that more quickly. I just want to comment on a method that we recently worked on with my collaborators. So perhaps by now it has become clear that in this whole population analysis business, what we do is to test a lot of models and see what happens when you do that. And one of the big problems is that these analyses will become more and more expensive as you have more events. And for accuracy requirements, you find that the cost of your analysis increases as more than the number of observations squared. It's not even linear, and it's more than quadratic in the number of observations. And so the idea that we had here is perhaps instead of repeating all of the analysis, testing a model with 1 peak, 2 peak, 3 peak, power law, broken power law, so on, you could do one first non-parametric analysis where you would, that would take some time, but then you would be able to remap the result of this non-parametric analysis into any other model that you want, instead of having to repeat the analysis from scratch. And so the idea is that in the second step, because what makes the analysis very expensive is to take into account selection effects and measurement errors. In that second step analysis, you wouldn't need to take those into account, and that would make the analysis much faster. And so, okay, perhaps I will skip on this because that will be perhaps a bit indigenous now, but this is just the formalism for which we do this whole remapping technique. And I will show directly some of the examples that we have. So here is on a very simple Gaussian data case. So you have the true distribution here in black. These are two different approaches that we use to do this, to apply this formalism. in each case, the shaded areas show the non-parametric reconstruction, and well, okay, it's hard to see, but essentially, the point is, once you do if you apply this remapping technique between your non-parametric reconstruction, and then you try to see, having applied this non-parametric reconstruction to a Gaussian model, so you say you now try to fit a Gaussian to your original data, these are the posterior distributions that we obtain for the parameters of the Gaussian. So this would be the mean, this is the variance. The green is showing you the direct inference, so if you apply the standard formalism to obtain the distribution of the mean and the variance. And the blue and red are showing you the results that we obtain with this method. So you can see that what we obtain has slightly broader errors, which is expected from the way we do it, but that it's very much compatible with the true value, and more importantly, the results from the direct analysis. In this formalism, so we have the parameters of the model that we try to infer, but there is also the other parameter that we introduce here, this beta, which is sort of a measure of the quality of fit of your model. And this here shows you how this quality of fit measure performs. So now if you take this Gaussian data and you try now to do this, so you do this non-parametric reconstruction and then try to apply this remapping to different types of distributions. So a uniform distribution between here, a Cauchy exponential distribution, so those are all models that, well, clearly don't match a Gaussian. And you can see that the beta that we obtain, so this quality of fit measure, is much lower than what we obtain when we use the true model, the Gaussian. We also consider the generalized Gaussian, which is sort of a broader class of distribution, which includes the Gaussian. And so since it can also reproduce quite well the data, because well, it does include the Gaussian, we obtain a similar quality of fit than when we're doing the Gaussian directly. And so, in a sense, so it's not exactly a base factor that people often use, because it doesn't include, for instance, the dimensionality penalty. It's measuring how well does your remapped model describe the data that you have. We also applied it directly to non-parametric, so to more parallel plus peak data, so more realistic astrophysical data. So this is data that we generate from the best fit parallel plus peak of the LVK. We consider 100, 3,000, 10,000 events. And this is how we reconstruct every time, so the mass distribution. And well, the point is that essentially we can reconstruct quite well after remapping the true distribution. And this is comparing this quality of fit factor between the power law plus peak, and if you remap onto a single power law without peak. And you can see that, well, independently of the approach that you take, so the more you're on the right side of this plot, the more it means that you favor the power law plus peak to the power law only. And as you have more and more events, you become clearly able to say that it's a power law plus peak and not just a power law. Well, this is just to say, essentially, we also perform some statistical tests, or some PP plots, and we find that, again, as the number of observations increases, this method becomes efficient at reconstructing the distribution. The problem is actually not in the not in the remapping method itself, because you can show analytically that it converges to the right solution. It's more the quality of the non-parametric reconstruction. So if you have too few events, the non-parametric reconstruction have very broad error bands, so on and so forth, and so this is what makes all of your PP plots not so well behaved. Okay, so well, I skim a bit quickly through that, but the conclusion I want to make is that, well, the current observation LIGO, Virgo, Cagra are bringing us some really totally new information on the population of stellar mass black holes in the universe. With the current data, we already have found some features at 10 and 35 solar masses, perhaps also some more. We know that the rate evolves with redshift, but redshift 1, and we have some interesting correlations in our data, but essentially, well, we need more data to understand this better. Well, I also discussed the fact that when you want to compare now the predictions from your astrophysical simulations to the data, you need to take some care in doing that so that you're not extrapolating any information from your data. And well, I did quickly through that, but I think that such remapping techniques that I mentioned could be very interesting in the future to speed up and so that people can much more easily test many models once we have some hundreds, thousands of observations. Also, something that I just want to highlight is that this technique that we use, this remapping technique, is actually extremely general. It's not just for a population analysis problem. I think it's something that could be very much used for remapping any agnostic reconstruction into any model-specific model. And so also in the case of tests of GR, so on and so forth, I think that's something that could be explored. So thank you very much for your attention.
We interacted in quite a lot. So, yes.
So just curiosity, so data is coming next week. How long does it take to run your code when the data arrives? Just push the button and 30 seconds or more?
No, so the non-parametric stuff that I mentioned here, this correlation, I think will take a couple of hours, but yes, it will be fast. Okay. So yeah, stay tuned for the upcoming, I think it will be a flood of upcoming papers in the next weeks.
So if you give an online seminar when you're back in Milano, send us the link.
Okay, I hope there will be more there, yeah.
Didn't fully follow all the steps from this statistical procedure, but I think a lot of people in more the machine learning oriented communities, especially related to things like strong gravitational lensing, have thought a lot about these aspects of reweighting probability distributions to try to capture selection effects properly and so on and so forth. I can send you some name of papers because there they have this problem where basically they're trying to figure out what is the sort of training distribution that they should use to be able to train models so that LSST, when it finds 100,000 gravitational lenses, can infer parameters very quickly. But obviously, they don't know what that distribution is, and so they have to do some sort of reweighting to try to match to what the observed is versus what they have in their template bank, and so on and so forth. Okay. And it seems to involve very similar math, actually. So I can point you to some of those papers if that seems helpful.
That would be great, yeah. Thank you.
So there are papers in the gravitational wave community about reweighting with the observational effect too, and they usually borrowed from particle physics in neutrino observation.
So I mean, so I don't know if that's what we're mentioning, because we have also tried to train emulators where you would put in the selection function. I think the big problem is that our selection probabilities are very expensive to compute. And typically, if you want to train like your model, I mean, I know because like we had also work on things like that, and it becomes quite a pain. But well, I'm happy to see. Yeah. Okay. Okay. Yeah.
Okay. Let's thank Alexandre. By the way, he'll be here tomorrow at 5.
Yeah. Exactly.